Yo, welcome. Today I want to work on building an OS to post in my Twitch chat. So I thought it would be kind of fun to work through what goes into like making an OS. Specifically, like I don't really care about like making a full GUI. That seems like a lot of work, and I don't really want to do that. But I do think that it's like an achievable thing to do to like build an OS that's basically capable of like running a web server and interacting with it, right? If I wanted to build like a bare bones OS so that I could do something with it, how much work is that? And I thought a kind of fun starting point there would be to build an OS that can post in my Twitch chat. That seems like a kind of like reasonable end goal, and something that's like probably very achievable. And so what I want to start with today is learning what goes into building an OS. So the first thing that we need to do is we need to boot. And I think if we boot an OS today in a virtual machine and can get some output of it, that's like a success, specifically with the ability to understand what's going on. So today's goal, boot an OS in QEMU. And we're going to use the term OS very lightly. Maybe we should say boot a kernel is maybe a better description of what we want to do. So we call this is stream 2023-09-25. And so I've done some like pre-work here to get a compiler set up that will cross-compile because when I generate code, when I call like, let's pop this open. First of all, let's make this a little bit bigger. So if I go into like make a test directory for demonstration purposes, and if I go in here and I say like let's make a little test file, and I say like include standard input output so I can print, and then I make a main function that prints hello world with a new line. And if I go gcc-o main and I run this and I see hello world, what this is actually doing is it's doing quite a lot. If I install this application strace, oh, I already have it, sweet. I can like actually see everything that goes on in terms of like calls that are going to the OS. Importantly here, like we have this, let's see if we can find the hello world. Yeah, here, so we have this like write hello world. We also have all this like setup stuff, like starting the executable, setting up the stack, setting up memory limits, blah, blah, blah. But what's important to know here is if I actually look at this, we can see that I'm like linking against Linux specific libraries. I think I can't remember what this like Linux VDSO is. I remember that like the kernel is injecting some library into all applications for some like fast version of get time or something. I wonder if this is easy to look up. So Linux, oh, it's actually got like a man page. Very nice, very nice. So this is a virtual dynamic shared object. Yeah, kernel automatically maps up address space to all user applications, because some things are slow. What does it have in it? Yeah, so it has stuff like get time, because like that's something that happens very often, and we don't want to have to go through like this is call overhead over time. Anyways, point is, we're linking like libc, which is an abstraction around a bunch of Linux syscalls and Linux VDSO, and our application won't be running in a context where these things are available. So the osdev wiki has told me to set up a cross compiler. That's basically like it still targets my CPU architecture, but it doesn't link against Linux. And so I did some pre-work to get that set up. I think it's working. If it's not working, we're in for a really boring stream because you're just going to be watching me compile. But hopefully it works to the point where I can run through this bare bones setup and kind of see if I can understand what's going on here. So I've read that the osdev wiki is a really good resource, so that's kind of where I've started. I don't actually know if that's good or not, but we'll kind of find out as we go along, which will be kind of fun. And so let's just kind of jump into it. So it looks like they're getting us to set up like some bootstrap assembly that has some magic or some like, what's this dot set do again? I think it like dot set GNU assembly. What does this do? Modifies value at address, right? So it's setting some values at addresses to these specific things. And where do these come from? Align. Oh, are these macros? Ah. So if I... Yeah. So these are declaring constants. So this is basically setting macros that I assume won't be compiled into the binary except for at use. Here we are creating a multiboot header, which, if I remember correctly, do I need to set linker flags here? Yes. Okay. So in my assembly, I say, hey, I am now the multiboot section. Everything after me is going into this section called multiboot. Now, normally, if I remember correctly, you would, yeah, right. When you put like code, that goes into like the text section. Is there a way for me to like check if I disassemble this like test binary? Is it object.d? Yeah, this is what I'm looking for. So all of the like code ends up in this like .text section. I think that this is part of like the elf spec. I don't remember, but like functions live in here. And if I were to have like, yeah, let's edit this really quick. If I were to have like a static int x, and I were to like in here increment this choice, so I could say like hello world, the first thing, and then the second thing, and in here I say x++. Let's try compiling that. Hello world 1, hello world 2. And I think now if I disassemble this, I should see like a section where that like static variable is defined. But I don't remember how to check this. There's probably a way to see stuff in BSS, which I believe is static memory. Objump show BSS. Here we go. This looks right. So what do those flags do? Man, objump help. So they're telling me to punch in -s, which is full contents, right? And -j is probably section for some reason. -j section, yeah. So objump -s-j bss main .bss. So I was under the impression that these section blocks set where I'm writing to. So here I'm starting to text and putting my functions, and in other places, like this should be setting like my memory. And I thought that my example of sticking a static int in there and using it would I would be able to see that in the BSX section, which is like static memory, if I recall correctly. But I guess maybe not. So that could be like maybe a mistake on my part or a misunderstanding. But I think at the very least, I think I'm correct in that these sections just say like, where am I writing to? And then, so that in assembly, I say like, I want this to go in the multiboot section. And I think if I remember correctly, you can like say these multiple times. So if I wanted to like put some stuff here and I want to go back to multiboot, I could. And then I think they'll like when I call, after I've like compiled my code, I have like these object headers with these sections. And then I think this linker script will say, now put the stuff I said at multiboot right at the front. So that the bootloader can find it. And then it like lines this linker script that they're going to have me run, I hope, will, how do I say this? Will like set where in the binary everything goes. Yeah. Okay, so they have this multiboot header, and they're claiming that a bootloader follows this standard. And all I put in here is the magic number that says, hey, this is a multiboot header. Okay. Flags. Okay, I guess I will have to look up this multiboot spec to know what these means. And checksum, sure, to prove we are multiboot. Okay, that makes sense. So let's look up multiboot standard and see if we can gather anything from this. Okay, so this is a standard, describes a bootloader. How do they load x86? Sure. Blah, blah, blah. Where is it? How do I find the standard? So on the osdev wiki, I want it to tell me, like, I want to know, like, where the flag, oh, multiboot specification. I wonder if I'm doing multiboot 1 or multiboot 2. Newer multiboot specification was created to solve the problems in the original spec. It's not backwards compatible. Okay, so how do I know which one I'm in? Does this say? It just says multiboot standard. Okay, let's assume multiboot 1 for now and just take a quick little peek. Okay, so layout of the multiboot header, magic, flags, checksum, which I think is what we have here. Magic, flags, checksum. Okay, cool. And then let's just like quickly glance at multiboot 2 and see if we have the same header. And if we don't, then we can be pretty sure. Yeah, okay. So this is not what we're writing. So we can be pretty sure that we're in multiboot 1. Okay. So how do I know what the flags field is? Flags field represents features of the OS, blah, blah, blah. Bits 0 and 15 to 15 indicate requirements. If the bootloader sees any of these bits set but doesn't understand the flags, blah, 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 it must notify the user. Okay, so how do I know what the flags are? Boot information format, flags. Okay, well, it would be nice to like see these documented somewhere. So let's take a look. So I'm doing align and mem info, which is saying provide a memory map and align loaded modules on page boundaries. Okay. So can I like search for align in here? Define multiboot header align. That's not right. Oh, here we go. Flags, so page align. Where do these come from? So I can probably find it in multiboot.h. Okay. So I think I saw multiboot 1 header file here. And somewhere in here, here we go. Here are the flags. Multiboot info, blah, blah, blah. Is there basic lower upper memory information? Is there a boot device set? Is there a command line defined? Are there mod? Okay. Is this right? Does this match what I see here? Magic? Flags, and flags are align and mem info. Align is 1. So no, this is not right. Let's look up align. Here we go. Multiboot page align memory info must pass memory information to the OS. Okay, so the bootloader sets up some form of memory and passes it to me, I guess. If I wanted video, I would ask for it, but I'm not for some reason. Okay. So that's not really, okay, sure. That makes sense. So grub, presumably, I think I saw it when I was reading this earlier. I think I saw something about grub. Grub will probably like search my disk for these like multi-boot header infos. And then since it knows that they're there, it will like do some work based on that. Okay, cool. There are magic values, documented the boot standard. Bootloader will search for the signature and the first 8 kilobits of the kernel file. Okay, aligned to a 32 boundary. The signature is its own section, so the header can be forced to be within the first 8K. Oh, I see. Okay. So if I had other stuff, if this was bigger, or if like other multi-boot stuff went somewhere else, it wouldn't be in the first 8K, so it would fail. Okay, sure. The multiboot standard does not define the value of the stack pointer register. It's up to the kernel to provide a stack. Sure, I guess arguably, I could use any register. I think it's well defined though in x86. x86 stack commands. If I remember correctly, there are just like push and pop commands which move ESP manually. Oh, okay, no, you do... Oh yeah, so if I push EAX, it will automatically adjust the value of the stack pointer by EX. I think that this is basically saying I move the stack down enough, like there's a pointer to the head of the stack, to see here, and as I add stuff, the stack moves. Okay, anyways. And then I copy my stuff in there. Okay, so the multi-boot spec does not say that it has to be ESP, but it almost certainly will be ESP. But we still have to define it ourselves. Let's read this some more. This allocates room for a small stack by creating a symbol at the bottom of it, then allocating 16K, 16K for it, and finally creating a symbol at the top. The stack grows downwards on x86, the stack is in its own section, blah, blah, blah. Sure. So it must be aligned, so we say, hey, this is my BSS. What is BSS? I thought BSS was static memory. So BSS section elf. Let's see if somebody can tell me what that is. Here we go. Block starting symbol. I've never heard that before. Statically allocated variables. Okay, so basically we're saying like we're gonna have our static memory here, and we want to be aligned to 16 byte boundaries. 16 bytes, yeah. Then we say, here's our stack of 16K that we've pre-allocated, right? So we said, here's the bottom of our stack. Then just like, hey, GNU assembler, just like run past 16K of memory, and then this is where the stack top is, sure. Okay. Okay, and then does the linker script move these around anywhere? No. Not that I see. So that's interesting. Okay. So now we have defined a stack. Now, the linker script defines start as the entry point. So when I link, it said, I guess our executable somewhere will say in it the address of start, and that's where we want to go. Maybe that's just like the first line in the text section, right? Like if I look at objdump here, if I were to just jump to text and start executing, I would just be in the start function of my executable. So we can maybe assume that for now, but I'm not positive about that. We'll think about this. I'll come back to that. But sure. So we've set up our stack. We know that we want to jump to start. So we say, hey, this is the name of our, hey, export the label start so that it can be seen externally. Oh, I didn't know about this type. I've never seen this before. GNU SM type. So why would I do this? I thought that I could just make a label and there, like, I didn't have to do anything else for that. So why would I do this? This is the type of symbol name to be either a function symbol or an object symbol. Oh, I guess because it could be anything. And so if I think it's like if I run nm-c main, there are these like letters here that say like, where do I see it? So like main is a function, init is a function. These like capital T's mean functions if I remember correctly. How do I, where do I find, here we go. Yeah, local text symbol where text means function. And these like letters mean, oh, this is a global, this is something in BSS. Okay, so I guess arguably I need to tell it its function, although I would think that if it was in the text section, it would automatically figure that out. So I don't really understand why this exists. The type of symbol named to be either a function symbol or an object symbol. There are 5 different syntactics supported, blah, 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 because some of these characters are used in substance. Okay, but like why? I don't, like from the perspective of the CPU executing, does it care? I would think no. Okay, well, let's just kind of gloss over that for now. Maybe part of the experimentation is that we can smack that out and see if this still works. What does the at here mean again? Oh, it doesn't matter. They're all the same. Okay. Back to bare bones. Let's get this out of here so I don't accidentally open it. Okay. So now we make a start function. So we set the stack. So we say like, hey, stack pointer, go to this like chunk of uninitialized memory. Do what you want. When I push in there, you're not going to like overwrite part of my code. Okay. What does it say? Bootloader has loaded us into 32-bit protected mode. Okay. Interrupts are disabled. Oh, nice. Okay. That makes my life easier. Paging is disabled. The processor state has been is defined as in the multiboot standard. Okay. Kernel can only make use of functions and code as it provides as part of itself. There's no printf, obviously. Yep, unless the kernel provides its own. Blah, 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 blah. Yep, okay. So we set up our stack. So now when we enter a function, something will like, we're overriding like a defined part of memory. Blah, blah, blah. Okay. So we set up high level processor state. Probably because doing assembly is straightforward. Why? So this is a good place to initialize processor state for the high level crucial. Okay. Why? So the processor is not fully initialized yet. Floating point is not set. The GDT should be loaded. Global, is that the interrupt table? GDT. I686 maybe. What is GDT x86 maybe? Global descriptor table. So if I assume that this is like the interrupt table. Oh gosh, this is a lot of info. Global descriptor table. Let's see like the high level Wikipedia answer. Table of 8 byte entries. Each entry may refer to a segment descriptor, local descriptor table, call gate, transferring control between privilege levels. Oh, I see. So this is probably used for like switching between like user and kernel mode. I'm sure it does a lot of other stuff. Okay, sure. We'll come back to this later too. There's a lot we don't get yet. Right, so now we call the main function from our kernel, and I like how they call it high level, which is, I guess, probably C has a kernel main in there. Okay, so there's really not much going on here. And then what's this have? CLI halt jump 1B. What does jump 1B do? Jump to the hit instruction if it ever wakes up due to a non-maskable interrupt occurring due to system management mode. Oh, the halt instruction. Oh. I see. Okay. If the system has something... Oh, I see. So after our main exits, we disable interrupts, we halt. And if we ever get an instruction, then we go back. Okay, so there's nothing actually too crazy in here. This is pretty straightforward, I guess, by some metric of straightforward. So that's pretty simple. Yeah, bootstrapping, fine. I'm okay with that. So now their main is writing to the terminal through. Oh, sure. Okay, so they have this like predefined VGA buffer. What is VGA again? I guess, is that like the cable? VGA text mode. Okay, so this kernel uses the VGA text mode buffer to output the device. It is a simple driver that remembers the location of the next character in the buffer and provides a primitive for adding a new character. Notably, there is no support for line breaks. Right, because you would have to move the cursor by a lot. And no support for scrolling when the screen is filled up. Okay, sure. So, is there anything interesting going on here? I think it's literally just they're taking the... I assume that there's a predefined width height in VGA, maybe 640 by 480. No, 80 by 25. Where do these come from? Maybe these are defined somewhere. VGA 80 by 25. VGA text mode from Wikipedia. Okay. Blah, blah, blah. How do I know the size? 80. There are modes of the character box width of 9, however, the 9th column. See, so how do I guess they set it to the mode that has 80 by 25. So I think I saw initialize. So set the color. So nowhere do they like initialize. Yeah, nowhere do they like set the mode of the VGA. So how do they know? There are modes with a character box width of 9. The default 80 by 25 mode. So there are probably other modes, so I could probably change it if I wanted to. Okay. So, yeah, nothing in here is crazy. So after we set up this is clear. We set the color, sure, whatever, which it sounds like just isn't used here. So, okay. Then they write a string where they punch the data in with Sterling. Ugh, gross. C strings. I hate Sterling. Okay, and then here they put char, and the put char probably, is it tracking terminal column, terminal row? So these must be statics. Right, yeah, so they just throw all this up here. Okay. Yeah, nothing too crazy. And then at the end, they have this linker script. Begin putting sections at 1 megabit. I don't understand. This is confusing to me. So I guess, I wonder if these are just being put into memory at exactly the memory location here, which would explain this like 1 megabyte jump, right? If the bootloader is allowed to take up to 1 megabyte in RAM, and they're just saying like, hey, all the rest of your program could be at 1 megabyte later. You might waste a meg, but whatever. Maybe that's what they're doing here. So if we assume that, I wonder if there's like a way for me to learn about this linker script sections. Blah blah blah. Okay. The job of the linker is to take all objects and libraries, blah blah blah, and put an executable. Sure. So the BF sections command provides two outputs, the blah blah blah. And so they put their vectors in their text. But like why would I jump this 1 meg? A conventional place for kernels to be loaded by the bootloader. I wonder if I can search this. This is like a pretty common. This is a pretty like user heavy wiki, so it would be interesting to see why. Okay. So maybe Grub just like takes the executable and just says like, hey, boom, here you go. All right, well, yeah, I'll do some Googling about this later. I don't really want to waste time Googling this. So I'm just going to assume that Grub is just dropping this in direct, like the text block in directly at the memory address. Because it would make sense, right? If I'm, right. Okay. So if my executable has an object at a specific memory address, I might expect that I can access that as like static memory. Right? If I have like a static memory, say like this terminal column, right? This is like a value in memory in BSS, and my executable needs to be able to access it. And how is it going to access it? It's going to access it by like looking at like using the address. So in here we get like a name for it, but when we run the linker has to resolve those into addresses. Now, if all addresses were relative, maybe it wouldn't matter, but if I remember correctly, you need to like specify that you want relative addresses. So I think my guess here is that we have the bootloader running in the first megabyte of RAM, and our executable expects our terminal start to be at a specific address, and so we skip the first megabyte because we don't want to like overwrite the bootloader as we are loading the executable. That makes sense to me, which would make sense why they're saying that this is by convention. That's my guess, but I don't know. I'm just guessing. So we'll come back. Maybe we'll find later that I'm totally wrong, but for now, that's the guess. Okay, so then we stick the multiboot header, as it's required to be very early in the image, or the bootloader won't recognize the file format. Let's think about this. This is 1 megabyte in, and this needs to be within the first 8K of the kernel file. Ah! Okay. So they know, so the bootloader knows. Oh, interesting. Okay. So if I wasn't using the multiboot standard, this would just be text, and I would say just jump here. But the multiboot standard is assuming that code starts at text, and they're assuming that the multiboot header is at the start of that, right? So we're kind of like making an executable to be loaded by multiboot, and probably is not runnable without multiboot. Because if we were to just jump to the start of the text section, then it wouldn't work. So the multiboot header says like, hey, where does your kernel start? And if I find multiboot stuff in there, then I'll run it. But if I don't, probably, my guess would be that it just like continues anyways. And then we inject the rest of our code after that. And so the multiboot bootloader must know that it must know to like parse that part and then jump after it. Okay, then we have our constants. Read, write data. Oh, so initialized memory, uninitialized memory. Okay. Yeah. Okay, so nothing in here is crazy. So let's start just trying to compile a kernel and see what happens. I think this is like probably very doable. So let's remove this test project. We don't need this anymore. I did have osdev test already here, but all that's in here is literally just like an executable that I tried to compile with the new cross compiler. So here I just was testing before this that if I run GCC to output a object file with f freestanding, that it would work, and it does. So I think this LD library path probably also isn't necessary. Yeah, it isn't. Okay. So we can just remove everything here. And let's just get running by creating these files. And let's just kind of copy paste them in whole. For now. And let's make a build here. So we'll have boot.o comes from boot.s. And how do I can never remember the makefile rules. So this is going to use this. I'm going to set my cross compiler. I actually don't have to set my cross compiler, so I'll just assume that my path is already set correctly. And make has rule flags for I think you can do like %.o comes from %.s, and then you come in from like the thing on the right to the thing on the left or something. I don't actually remember what these are, so let's just kind of see what happens. Ooh, make not solved. Okay. So let's create a development environment here for my NixOS project. So what's going to be in here? So we have to import Nix packages. I think it's like this. And then we do make shell build inputs equals GNU make. I think they called it. Okay. Let's pop that bad boy open. Give it a sec. Okay. And then we'll say all depends on boot s. Okay. So makefile wildcards. I hate this part. I always forget. Makefile wildcard rules. Pattern intro. Okay. Yep. So why is this not working? Make. So there should be a boot. Oh. Beep beep. Okay, so now I have to set up my path correctly. So we'll for this project, we'll set up an environment script that sources I'll like source this manually, and it will just say export path is the same as my current path, but also with opt gcc cross bin. So now if I do source env make, okay, no such file directory, s686 elf as, hello. So why doesn't it like that? What the heck? Oh. It's probably this. Make. So this is running -o boot.o. Okay. It still doesn't like this. Make not respecting path. I wonder if this is some like bullshit NixOS thing that's like clearing my path. Which make. Oh. This is just the raw binary. Okay. So why is make saying that executable in path doesn't exist. Makefile executable not found. I'm missing something. See, because like if I just run this directly, it should work, right? Yeah, so I don't understand what's happening here. We have to do dot env grep path. Yep. I'm definitely missing something. Okay, but we'll deal with this later. So let's, for now, we won't use a makefile, and we'll make a build script. So we'll make a new bash script that runs this, and we'll come back to this later. So we'll make it executable, run it. Okay. And set -ex so that we see what's happening and that it crashes on failure. Okay. Now let's create our kernel main.c. So we'll call this kernel.c. And we'll add this command line to our build script. So let's set up a Git repo because I know I'm gonna type stuff that I regret. And in our Git, we should ignore everything that ends in .o. Okay. Cool. And if I build, fatal error cannot execute cc1 exec vp no such file or directory. So I was under the impression that this was working before. To see kernel.c -o kernel.o f freestanding. Okay, let's try this again. So I previously called these directly, so let's try that. That does work. So there's something odd with path as well, but that's okay. We'll deal with that later. So let's just set here, we'll set cross compile equals this, and then we'll call cross compile. And I think it's like this. Okay, let's see if that works. Oops, like this, sorry. The curly brace has to come after the $sign. Oops. Cross compile. Compile. Okay, there we go. There we go. Okay. Everything's working. We're chilling. Okay. Now we set up the linker script, which we now also understand. So we call this linker.ld. Right, we just let it go crazy. And okay, we then stick this into the build script like this. And we paste in the same cross compile. All right. So we now have the binary for our kernel. Very cool. Very cool. So I would be interested in if I can hex dump myos.bin. Do I see anything interesting in here? Oh my gosh. Hex dump. Oh, how do I make this output like sane? Oh, big C, not little c, obviously. Yeah, nothing too interesting. Okay. Let's take a look. So we don't need GNU make in here anymore because we stopped using it, but we do need grub too, like this. So let's start with the environment. We'll pull in grub. And we'll check the output here. So that exited 0. Oops, who taught us about example? Kernels. Oh. Right, so this exits 1 if it's not, and 0 if it is. So this is great. And now we have to create a grub config to load our OS. Okay, so nothing crazy here. We have a menu entry in grub, and we say, hey, grub, this is a multiboot file. Please boot it if this entry is clicked. And then what do? They make an ISO. Oh my gosh. Okay, so we like build an ISO out of the binary in the config. Okay, sure. So let's copy paste all this. And then we'll build, right? So we have to make the grub config still, which was this guy who's just saying multiboot me please. XOR ISO is not found. So we just add that guy to our dev environment. Hello, what's going on? Here we go. Pop open the environment again. Okay. So now I have myos.iso. And let's just make sure that we correctly set up the git ignore. So myos.iso, or I guess star iso star bin. And isodir. There we go. So now all that stuff is what we want to be committed if we were to commit this. And now let's try booting it. Bump, 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 bump. Okay. Oh, sick. Oh, sick. That's so cool. We're here. Okay. So yeah, that's sick. So let's add QEMU here for testing to our dev environment. Bump, 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 bump. Okay, so I run build and QEMU on the ISO. That's sick. And then let's just confirm that if I were to do something like edit this so that this doesn't say hello world, but it says like, we did it. We don't see what we expect here. So why is that? Isodir. Oh, because I didn't create the binary in here. Where is... Oh no, I did. myos.bin, kernel o. So why did this not fix anything? Oh, we don't even need... Okay, so that's a bug. with the grub part. And it also seems like, actually, for now, we can get away without setting up grub. Okay, but let's try this again. So I cleaned that, which means that... Yeah, okay. So after clean, we do in fact get that we did it. Okay, so that's pretty cool. We now have a executable built in C that is bootstrapped by our assembly file and writes to the terminal. That's pretty cool. I think I'll call it for now. That's kind of what I wanted to get done today. I know all we did is copy paste, but I think that like the intuition that we built on what's happening is pretty good, and that gives us like enough to move forward. So we know that we can create an OS kernel, whatever you want to call it, and I want to do some like offline reading on what to do next. So if the goal is to generate something that can like speak to the network, I have to understand what like the next steps are and like how to get QEMU to initialize the network stack and what we need to do from our OS to work in it. I might also experiment offline with like getting I'm curious, like, do I need to be working in C? Probably not, right? Anything that I can use LD to link and can create a start function in is probably good. So if I wanted to go crazy and start writing my OS in Rust, I bet you that's possible. Do I want to try that now, actually? Is that boring? Yeah, maybe I'll give it a quick shot off camera, and if I like where that goes, I'll come back and show it. Okay, yeah, so thank you for watching. This has been fun, and we'll keep going with this tomorrow. Thanks. Bye.